Welcome to lecture thin film interference. After this, you should be able to calculate the interference in thin films, calculate the change of phase due to the path length difference, reflection, and index of refraction. Now, you've seen this phenomenon, probably didn't even know what it was. It's beautiful, actually. And if you have like a soap bubble or gasoline spilled on a wet street or from the wings of various insects, you can often see a spectrum of color that reflects from these things. And some bird feathers actually seem to change hue as the bird moves, and insects do the same thing. The colors seen in thin films are produced by the selective interference in the films of the light waves and mixed frequencies. Iridescence is the interference of light waves and mixed frequencies, which produces a spectrum of colors. A thin film, such as the soap bubble, has two closely spaced surfaces. Light that reflects from one surface may cancel light that reflects from the other surface. If the film is just the right thickness, it could cause, say, the destructive interference of blue light. If the film is illuminated with white light, then the light that will reflect to your eye will have no blue in it. Instead, you will see the complementary color of yellow reflected. The blue light doesn't disappear. It gets transmitted through to the opposite side of the film and can be viewed there. So the complementary color appears in the reflected light. In a thicker part of the film where green is canceled, say here, the bubble will appear magenta. The green is on the other side. The different colors correspond to the cancellation of their complementary colors by different thicknesses of the film. This is, of course, the film is sagging here because it's held vertically, and because it's liquid, it's going to sag down and get thicker down at the bottom here, and that's reflected by all these different bands of colors. For a thin layer of gasoline on a layer of water, light will reflect from both the air gasoline interface and the gasoline water interface. If the incident beam is monochromatic blue and the gasoline layer is just the right thickness to cause cancellation of the light of that wavelength, the gasoline surface will then appear dark. The blue light will go through into the water. If the incident beam is white sunlight, then in this circumstance, the surface would appear yellow. And of course, as I said before, the blue light gets transmitted through the film. Different films and parts of film may selectively reflect and transmit different colors depending on the wavelengths, thicknesses, and reflective phase shifts. Now, when light is incident on a thin, transparent film in air, the light waves get reflected from the front and back surfaces, and they can then interfere. So here's a picture of this. We have an incident ray coming in. Some of it goes through, and some of it gets reflected off the first surface. The stuff that goes through gets reflected off the back surface. Now, not shown here is there will be probably some that gets transmitted through. Now, for near normal incidents, the wavelength conditions for maximum and minimum intensity of the light reflected from a film with air on both sides are 2L equals m plus 1/2 lambda over n2 for m equals 0, 1, 2. And this is for maxima. In other words, what you would see in the reflected light. L, of course, is the thickness of the film. N2 is the index of refraction of this middle medium. The other part would be the minima, and that would be 2L equals m lambda over n2 for m equals 0, 1, 2. Now, the minima on this side will be the maxima on that side. These equations work whenever n2 is greater than the refractive indices of the surrounding material. So in other words, a thin film in air. The phase difference between the two rays completely rules what you see. These phase differences can come from reflection, path length differences, differences in the speed of light, that is the index of refraction of the various media. All of the reflected rays and this transmitted rays are actually derived from the incident ray, but they undergo different paths and conditions. R1 reflects on the first interface and may undergo a reflection phase shift. Ray R2 will reflect from the second interface, also translits 1, 2L for path length difference, and may undergo a reflection phase shift. Ray R3 passes through the length of this material, L of the second material, may undergo phase shift due to varying light speed in different materials. Ray R4 does a little bit of extra here. It goes through here, bounces off this surface, bounces off that surface, and comes out again. Now, this will pass through 3L of the second material and undergo 2 reflections. Differences between these rays may set up the interference in what you see. So these two would interfere with each other. It may set up the different colors you see. These two, the transmitted rays, can also interfere with each other and set up different colors. Now, refraction at boundary cannot produce a phase change. Reflection can. depends on the indices of refraction of the two media forming the boundary. If you were reflecting off a lower index, there is no phase shift. If you're reflecting off a higher index, there's a 1/2 wavelength phase shift difference. And the way to remember that is higher n equals 1/2 lambda. So higher n equals 1/2 lambda. And this, you can sort of illustrate this with rope. You've got thick rope. That means the wave will be slow in this media. So effectively N1 is greater than N2. And of course, this would be thin string. The wave will travel much faster in the thin string. And what will happen here is that you end up, if you send a pulse down the rope and the other end is tied to the string and then to a doorknob, say, the pulse will come back and it'll come back in phase with the incoming pulse. If instead you have string here, rope here, string here, rope here, so N1 of the string is going to be less than N2. And when you send a pulse down that, it comes back off this interface here, I think 180-degree phase shift, or 1/2 a wave. So that's the reason it looks like it's upside down. Now, a wavelength of light in a medium is inversely proportional to the refractive index of the material. So lambda n equals lambda over n. And we're going to send two parallel, initially in phase beams into these two different media. And when they come out, there's a very good chance they will no longer be in phase, even if their path lengths are identical. Why? Well, they'd have different media. If they have different media, they're going to travel at different speeds. On top of that, the wavelengths will change. So we're going to count the number of wavelengths in material 1, and that'll be L, that's the thickness of the material divided by the wavelength, and that in the material. And also, and of course, remember, that's going to change. And that will then be L times N1 divided by lambda. For material 2, we get pretty much the same thing, but now we're talking about N2. So we're going to assume that N2 is greater than N1, and we need to find the difference. We're interested in the difference between these two paths. And we subtract N2 minus N1 equals L over lambda times the quantity N2 minus N1. If big N2 minus big N1 is an integer number of 1/2 wavelength, you have destructive interference. If big N2 minus big N1 is an integer multiple of 1 wavelength, then you have constructive interference. The first one is destructive, the second one's constructive. Now, usually you'll get an integer number of wavelengths plus some fraction. We're normally only interested in a fraction. A phase shift of an integer number of wavelengths is equivalent to no difference in phase. For instance, if you found a phase difference of 55.25 wavelengths, the waves would actually be out of phase by 0.25, or the wavelength over 4. The constructive interference occurs for phase length differences of my, where m equals 0, 1, 2. Completely destructive interference occurs for phase differences of 0.5 lambda, and that would occur at 1.5, 2.5, or m plus 1/2 lambda, where m equals 0, 1, 2. For a phase difference, but different than other of these, you get something between completely constructive and completely destructive. It's also possible to express phase differences in degrees of radians. A phase difference of 1 wavelength is 360 degrees, or 2 pi radians. Not only do we have reflected rays, but we can also have transmitted rays. And these can also go constructive and destructive interference. So for instance, we have ray 4 coming through here. It's gone through two reflections with two possible phase shift reflections. Its path is 3L. Ray 3 does not undergo any reflections. Its path is L. Now, for a thin film in air, if L is less than 1/10 of a wavelength, then the phase difference to the path length difference can be neglected. Because reflection phase shifting, the phase difference between R1 and R2 will always be 1/2 wavelength. This is destructive interference. The film will appear dark when viewed from an illuminated side. This is what's happening in the top of the lower picture. That's why that's dark. There is actually a very thin film there. The gravity tugging on this has made it thinner. The film will appear bright at the top when viewed from the other side because there's no reflection phase shift for the light going through the film. In the picture, you can see in the bands of color, rainbow colors, the variations of film thickness as gravity makes the lower part thicker at the very bottom. Colors overlap and completely fade away as the bands get narrower and narrower. As promised, I'm now going to derive the formulas for transmission through a thin film where N1 is less than N2 and N2 is greater than N3. This would be this classic case of a thin film in air. The first thing you want to do is make a table. The next thing I always do is make sure I check the drawing or make a drawing, and I want to make sure I'm looking at R3 and R4 because these are the ones that are being transmitted through the film. And I always do this. I always list the index of the surface that the light reflects from in the first part here. So I have N3 is less than N2. That's this one. And I also have N1 is less than N2. Notice that it's higher by half. When this one is smaller, and it's the one being reflected off of, this means there's going to be no reflection phase shift here. And ditto for this, there's going to be no reflection phase shift there. So you can look, when you list it this way, you can look at the directions of the arrows here. If they're pointing to the left, the phase shift due to the reflection is 0. They're both pointing to the left. So we have 0 reflection phase shift. Now you look at the path length difference. And remember, you're interested in the path length difference. Okay, so what you have here is you have this ray goes through, hits this point right here and splits. Part of it comes out and part of it bounces around 2 more times through two more paths, 2L. So it bounces 2 times 2L. That's the 2L. Ray 3 just goes straight through, and we're interested in difference. And that's where it splits right here. So you end up with a total of 2L, and you end up with 0 here. This means you need this equation for the maxima. 2L equals m lambda divided by N2. The out of phase one is just the other one. That will be 2L equals m plus 1/2 lambda divided by N2 for these different orders. Now, this means that the in phase one will have a certain colors. The out of phase one will have the complementary colors. So in other words, the one that goes through will have certain colors. The one that gets blocked out will be the complementary colors. These are the same 2 equations as for reflection through a thin film and air, but now reverse light for dark. The colors you see reflected on one side of the film are the complementary colors to the ones that you see in the same places on the other side of the film. Okay, now here's an example. We have N1 greater than N2 and less than N3. First thing you want to do is break this up and shift it out correctly. You want to always list the end that the light reflects off of first. So we have the same picture as before, and now the delta L for ray R1 is 0. For ray 1, there will be no reflection shift because N2 is less than N1, so it's bouncing off of the lower index of refraction. The arrow is pointing to the left, so this means this is 0. For ray 2, you have a 2L path length difference because it goes through, bounces off here. And you also have a reflection shift of 1/2 because N3 is greater than N2. So the total of this is 2L and 1/2. So the 2L goes here and the 1/2 goes there. In phase, we want 2L equals m plus 1/2 lambda divided by M2 for m equals 0, 1, 2. If it's out of phase, you just pick the other equation. 2L equals m lambda divided by N2, where m is the order number 0, 1, 2. Remember, these are for darks. Now, you end up with the same 2 equations over and over and over again, but they can be reversed. A glass lens is coated on one side with a thin film of magnesium fluoride. This is MgF2 to reduce reflection from the lens surface. The index of refraction of magnesium fluoride is 1.38, and that of the glass is 1.5. What is the least coating thickness that eliminates the via interference, the reflection from the middle of the spectrum? The physics of this is thin film interference. We're going to assume that the light is approximately perpendicular to the surface. We want destructive interference, that is the stuff that's out of phase. We write down the knowns and unknowns, being very careful of the units, make sure they're consistent. We check the n's and recognize that N1 is less than N2 and N2 is less than N3, which was example 3. Now, I'm just repeating this just for convenience. And now we have N1 less than N2 less than N3, and we use that to set this part up because it is reflecting off a higher index of refraction each time, so higher by half. Now we list the individual rays and their path length difference. Of course, ray 1 just bounces off of this, so it doesn't go through the medium, so its path length difference is 0. N2 is greater than N1, so there will be a 1/2 reflection shift here. Ray 2 will bounce off this material here, and it will go through a total of 2L thicknesses of the material. And of course, ray 2 is bouncing off a higher index of refraction, so it's going to have a 1/2 wavelength phase shift. We add these up. 2L equals 1. So what you have here is 2L on this side and M, just M, without this stuff, just M by itself, not M plus 1/2, M. Now that's for the max or bright, the ones that are reinforced. The out of phase will be the other equation, 2L equals M plus 1/2 lambda divided by N2. And of course, in this case, we want destructive out of phase interference because it's anti-reflection coatings. That means it eliminates the wavelengths that would otherwise be reflected. Okay, so for example, number 3, we want 2L equals M plus 1/2 lambda divided by N2. The algebraic solution of that, we're only interested in it will be this, L equals M plus 1/2 lambda over 2N2. Now we can stuff in some numbers. We want the 0th order. So we say M equals 0, and then just the rest of it just comes along. And of course, here's the 550 nanometers, and here's N2 of 1.38. It turns out it's 99.6 nanometers. That's how thick that film has to be to block this bluish green light. Now we have an interesting example here. Shown is a transparent plastic block with a thin wedge of air at the right. A broad beam of red light with wavelength lambda equals 632.8 nanometers is directed downward through the top of the block at an incident angle of 0 degrees. Some of the light that passes into the plastic is reflected back up from the top and bottom surfaces, from here and here, of the wedge, which acts as this air here acts as a thin film of air with a thickness that varies uniformly and gradually from the left side, where it's a thickness of L sub L, to the right side, where it's a thickness of LR. An observer looking down on the block will see an interference pattern consisting of 6 dark fringes and 5 bright fringes along the wedge. What is the change in thickness? That is LR minus L along the wedge. Okay, so this is the physics of thin film interference with reflection. The knowns and unknowns, reflection, and this N1 greater than N2, and N2 is less than N3. We know that N2 equals 1 because it's air. N1 and N3 are equal, but we don't know. And the wavelength is 632.8 nanometers. We have 6 dark fringes, 5 bright fringes. We have more dark fringes than bright. These have to go alternating. So that means the out of phase of the dark fringes are going to be at the end. 5 bright fringe. Each bright fringe adds 1 order number. In other words, this might be M equals 1, this might be M equals 2, 3. And the order number on the right side, that's over here, is going to be 5 plus the order number on the left side. So MR equals ML plus 5, or MR minus ML equals 5. Now we need to know delta L. We know that N1 is greater than N2, and N2 is less than N3. And this is example 4 that we did a few minutes ago. This is repeated on the next slide for continuity. So here is what we had before. We wound up with this equation for the in phase, but we're interested in the out of phase because we're looking at those dark fringes. So the out of phase is 2L equals M lambda divided by N2. Okay, so we know that 2L equals M lambda over N2. We can solve this for L. L equals M lambda over 2N2. And LL will be ML lambda over 2N2, and LR will be MR lambda over 2N2. The delta L is just going to be subtracting these two from each other. If we pull out some of the common terms, we wind up with delta L equals lambda over 2N2 times the quantity MR minus ML. And we can play with this a little more. We find out that delta L equals 5 lambda over 2N2. The 5 here comes from the fact that MR minus ML is 5 because there are 5 dark fringes between the right and left side. Delta L is 5 times the wavelength of 632.8 nanometers and 2 times the index refraction of air. And this then becomes delta L equals 1.58 times 10 to the minus 6 meters. So that's the variation in thickness between one end and the other. And this is a very accurate way of measuring tiny differences in thickness. Now, 2 light sources emit waves of lambda equals 1 meter, which are in phase. The 2 waves from each source meet at a distant point. Wave 1 has traveled 2 meters to reach the point, and wave 2 has traveled 3 meters. When the waves meet, they're going to be in phase with each other because they are 1 wavelength different from each other. Consider 2 identical microscope slides in air, and they're illuminated with light from a laser from above. The slides are exactly parallel, and the top slide is moving slowly upward. What do you see from looking down from the top view? Actually, we're going to see is it first be black, then bright, then black, then bright, then black, then bright. So what's going to happen is as these things move apart, the path difference between the interfering rays will change because of this thickness of this film is constantly changing. And thus the phase between the interfering rays will keep changing, alternately out of phase and in phase and out of phase and in phase. Thank you.